At our definition now of crystal lattice, we know it must have a pattern and form like this. So that's why they say orderly, right? It must be neatly packed together. So metallic bonding, now we have another definition, metallic bonding. Okay, this is the bond between positive ions and delocalized valence electrons in a metal. Obviously, because the definition is for metallic bonding, and metallic bonding forms between metals. So, now we get this, we all know what positive ions is, right? Cations, yes. So it is cations, and as we know from the periodic table and all the work we've done so far, metals would form positive ions. Okay, so if you're unsure in the definition when you write the exam, just think about your periodic table. Your metals form positive ions. Okay, so it must be between a positive ion and our delocalized electrons. Okay, now we get to the word delocalized. So if you are a local of Paris, what does that mean? A local of Paris. Local. Yes, it means you live here, you're from here, you go to school here, you wash your toes here, right? You live in Paris, you're a local of Paris, okay? But as you guys probably know, this is a very touristy place. So there's people that come down from Joburg for the weekend, right? And you also go on holiday. So when you go on holiday somewhere else, right? That means you are not in your local place anymore, right? So you're delocalized. Okay, so you're not in your local area anymore. You're not in Paris anymore. You went to Joburg or you went to Durban or somewhere. So you're not in your local place. You're not in your hometown anymore. Okay, so then you become delocalized.
So the electrons visit each other?
Sort of. We will get to that now.
So I'm delocalized.
She lives in Frankfurt.
Yes, you're delocalized when you come to school, yeah. Okay, so what happens in metals, right? Is because, let's draw another diagram here. Okay. So if we have our crystal lattice of our metal positive ions. Okay, so these are all positive ions. If you draw this, the circles must just overlap a bit. Okay, so what happens here is we know we have our electrons around our core. And our core is positive. The nucleus of our atom is positive. So we know the electrons move around the nucleus. Okay? So what happens when this electron comes down here? Now this electron is closer to this nucleus, this positive charge. And as we all know, positive and negative attract each other. Okay? So what happens then? Because it's closer to this nucleus, then it turns around and starts going around our other atom. And now it's closer to this nucleus and it moves around like this. And then it goes like this through the whole structure. So we had an electron from our first atom, right? And now it's in its local position, right? Because it's originally from this atom. But now it starts to orbit one of the other ions, one of our other nucleuses, right? Then it becomes delocalized, right? Because it's not at its original atom anymore. So what happens in a metallic bonding is that all the valence electrons of all our atoms move around. They don't stick to its atom anymore. They move around everywhere in this crystal lattice. Okay, so it's a delocalized sea of electrons because there's so much of it, and that we can see in this picture over here. So we started with our electron over here for this positive, for this nucleus, And as you can see, it moved around, okay? This one moved around. They all move throughout our crystal lattice. Okay, they don't stay in the same place, yes?
So then in the exam, are we supposed to do it like this or circles are supposed to go in that?
Sorry, just say, oh yes, you won't be asked to draw this. Okay, so this is just to explain to you guys what happens, right? So let's read some here. Metals are usually solids, okay? They are usually solids with their atoms packed tightly into a metallic crystal lattice. And this happens so that the outer orbitals overlap, right? Because that's where our electron is moving, and now it's closer to the other nucleus, so it moves around that nucleus rather, and so forth. But it happens to all the valence electrons in a metal. Okay, so each metal atom loses control of its valence electron. Okay, so it can't control that valence electron anymore because now over here it is closer to this positive nucleus. So this atom loses control of this electron when it starts to orbit the other nucleus. Okay. So these free electrons now, they're not attached to their specific nucleus anymore, okay? They form a sea of free electrons, okay? And we say the electrons are delocalized. They're not at their original atom anymore. Okay, and because they lost their electrons, the metal becomes a positive ion. Alright, so here we can see each of these atoms lost an electron that's moving around the inside of our crystal lattice, and then it becomes a positive ion. Okay, so a metallic bond. Right, this is the section we're busy with, our first type of bond. Okay, they are made up out of positive ions and they're held together by a negative sea of electrons as a type of electrostatic glue. Okay, so electrostatic just means our positive and negative attract each other, right? Okay, so because of this sea of electrons in our metal, okay, they hold the whole metal together. Okay, so our sea of free electrons can move under, okay, so our electrons, our free electrons can move under the influence of a potential difference. Okay, do you guys remember what a potential difference is? Okay, what's the potential difference? No, it's okay. Just explain it as you remember it. Yes. Where do we get that? Yes, we get it in circuits, right? Our battery provides a potential difference to our whole circuit. Okay, so now we get a bit into the chemistry of why this works. Okay, so the metal conducts electricity, right? So electricity or current is just the movement of charge, right? You guys learned that. It's charge that's moving throughout our circuit. Okay? That's why metals are such good conductors, because their electrons are free. They can move throughout our metal, right? And actually create a current. That's interesting, right? Now we know a bit more about how the electricity flows. Okay, because the electrons are free in a metal, so the current will flow. Okay, so electrons can also transfer heat by carrying kinetic energy through the metal. Okay, so have you ever, for example, touched a wire or something and then it was hot? Okay, so that happens because the electrons that move through the metal now collide with one another, or they collide with our positive ions. Okay, and if we collide, there's a transfer of kinetic energy into heat energy. Because of these collisions, then our wire will warm up. Okay, so they transfer heat by turning their kinetic energy into heat energy. Okay, so that's what this sentence means. And then the last one. So metallic bonding allows metals to be malleable and ductile. What does malleable and ductile mean? Yes. Yes, okay. So also definitions that you must know for the exam. So because our electrons are packed, or metal atoms are packed in the crystal lattice. If we take these books, for example, right? If we take this sketch down here, and we say this is one book, this is another book, and this is the other book, you get the idea, right? So one book represents one row. So what happens when I push this book? Okay, it will fall off quite easily. It doesn't take a lot of force to move these books, right? Mm-hmm. That's why metals are so malleable and ductile, is because of the crystal lattice formation we find in metals. Okay, you understand that? Yes. Okay, so this is just an example. So if we read down here, the outer electrons are so weakly bound to metal atoms that they are free to roam across the entire metal. Having lost their outer electrons, our individual metal atoms are more like positive ions in a swarm of communal electrons. Okay, so what this sketch means is, if we take this electron over here, for example, then this redded out area here represents the negativity of the electron. Okay, so as we can see, if we do that for each of our electrons here, we get this electron cloud of negativity throughout our metal. And that's just what is explained in this sketch, right? So each of these electrons contribute to a redded area, so redded out the red gradient here. And as we can see, for example, here where there's no electrons, we have there's no part of an electron cloud there.
Ma'am, can these things be seen the negative and positive?
No. Okay, so that is what science is, right? So when we looked at how a atom is made up of, right? Okay, so there's a few things we definitely know. We definitely know there are protons, we definitely know there are neutrons, and we definitely know there are electrons.
Do you know that they're in a circle?
Yeah, okay, so we know the core exists out of our protons and our neutrons, and we know the electrons are around our nucleus, okay? Because through different experiments, we made these deductions. For example, you remember the gold foil in the video that I showed you. There was this, let's just see, a ring like this, and a gold foil here in the middle, and then this is bombarded with our helium atoms. And because helium atoms are so small, and the gold atoms are so large, we expected it to just go right through. And then we can see where our helium atoms collide with the metal. We can see it on this outer ring. It makes a little mark if a helium atom connects there. But then they saw, no, was one that collided over here, there was one that collided over here, one that collided over here. And from that, they deduced that our positive ions is in the middle, right? Because when they collided with the gold atoms in the gold foil, okay, if they collide with the correct orientation, our helium atom will be deflected, and we will see a mark on the side of our outer ring. Okay, so we can't usually see these things. We can't see atoms. We don't have microscopes that can go so small, right? But we use experiments and see what the atoms do and deduce how they look. It was everything we did on the first page of the previous chapter, I think, when we learned all those names like Heisenberg and Pauli and Rutherford and Niels Bohr. So if you go look at that video again, the video that's linked on that page, you'll see some more of the experiments and how they got through to the model we have of an atom today. Okay, so that was our metallic bonds. Next we have covalent bonds. Our covalent bonds, okay, very, very important. Oh, not important. Important. Okay? Because that's what a lot of questions are asked about, is about our covalent bonds, because there are so many of them, and each of them is a little different. It's not like our metallic bonds, right? Each of them is a little different. And because we have so many possibilities, right? Okay. So covalent bonds form between what again? Non-metals and non-metals, yes. Okay. So a covalent bond, the definition of a covalent bond is the sharing of electrons between atoms to form molecules. Okay. So now we get to why drawing the orbitals were important. And knowing a metal likes to lose an electron and a non-metal would rather gain electrons. Okay. So we're going to get to that now. Let's just look at some of the properties. Okay, covalent bonds form between non-metal and a non-metal. And electrons are shared between two atoms, at least two atoms. And they do not conduct electricity in solid or molten form. What does molten mean? Liquid, yes. If you have ever heard the term of molten lava, yes. Liquid. Because lava is a liquid. It's liquid rocks. Okay. So let's look at the hydrogen molecule, for example. So two hydrogen atoms each contain one unpaired valence electron in the 1s orbital. Right, we know this. We've drawn this, and hydrogen is our most plane of the atoms. Okay, so here we can see we have two hydrogen atoms, and each have one electron in their 1s orbital. Right, you understand this part of the sketch? Okay, because we are going to look at how two hydrogen molecules bond with each other. So first we start with them apart, they're not together yet. And we have one electron in the 1s orbital of our first hydrogen atom and one electron in the 1s orbital of our second hydrogen atom. Okay, so you guys understand this so far? Okay, so when our molecules or atoms come closer together, right? Okay. Their two half-filled orbitals overlap. Okay, so they come so close to each other that our orbitals start to overlap with each other. Okay, this is what we can see in the sketch below. Right, we have our proton in the nucleus and we have our orbital where our electron is found. And then we add these two hydrogen atoms together, and then their orbitals, okay, they overlap, right? And we have this overlapping of orbitals. And then what happens next is the two electrons are attracted by both the nuclei, okay? So the electron in this orbital is attracted by both of the nuclei, okay? Because they're just protons, right? They're positive. So they attract both the electrons. I think I drew it here, right? So we have this electron that is attracted by that nucleus, and this electron that is attracted by that nucleus. But this nucleus also attracts that electron. So both of these nucleus or nuclei, right, attract both the electrons. Okay. So the two electrons then move around both the nuclei and form a very important word here or term is a bonding pair, right, in a new bonding orbital. So a new orbital forms, right, or new orbital over here, right, and these two electrons then share this orbital. Okay, now if we go back to our AFBO diagram, if these two orbitals overlap, what's going to happen? Right? We will get a one electron from our first hydrogen atom and another electron from our second hydrogen atom. Right? Now hydrogen is happy because it has two electrons in its 1s orbital. Its highest energy level is filled. It looks like helium now, right? Okay. So, this is a covalent bond. So, the two hydrogen atoms that share the electron pair now forms a covalent bond. So, as soon as these two atoms, no matter what it is, the non-metals of course, okay, as soon as they start sharing electrons, they become covalently bonded, which is our second type of bonding, okay? And they are more stable than the two separate atoms. You remember I've mentioned to you guys that atoms and molecules want to be in their lowest energy state possible. Okay? So together, our two hydrogen atoms together, they are more stable, they have less energy than the two separate atoms have. So they are much happier together than they are apart. Okay? It's like if you find your soulmate, right? You'll be happier with him or her, right? Than you are at being alone. Okay, they're happier together. So now we get to something important. And this you will have to be able to draw for exams. Okay, but we are going to practice it. So this is what we call a Lewis structure. Okay, or it's called the cross-dot method. But when we get to the exams, right, they're going to ask you draw a Lewis structure. Okay, it's the cross and dots method. So the first thing we do is determine the number of valence electrons of both the atoms involved. Okay, so we have hydrogen that bonds with another hydrogen. How many valence electrons does hydrogen have? One, okay. So hydrogen has one valence electron. Now we indicate the valence electrons around the atoms by means of dots or crosses. For example, if we add two hydrogen atoms together, we have our first one with the valence electron drawn as a dot, and our second one with the valence electron drawn as a cross. Okay, now we form a covalent bond. These two hydrogen atoms come close together that they share an electron pair. Okay, so they form a covalent bond, and it can be presented as follows. So we have our two hydrogens that we add together. We get an arrow to show that something happened, and now we have our hydrogen and both of our electrons written underneath one another. Very importantly, they must be underneath one another. Not next to each other, underneath them, right? Between our two H's, right? Between our two atoms, yes.
So now the X is always going to be on top.
No, that doesn't matter. It doesn't matter which one is on top or which one is on the bottom. It's just to show that it comes from another hydrogen atom.
Therefore, can we do both of them dots or both of them crosses, or we have to choose?
Okay, so mostly it is, it doesn't matter, but for you guys, do the dots and crosses. One dot and one cross, okay. So now we get a second type. I just want to, this is not number 4, it's not part of our Lewis structure, it's something different. Okay, so the bonding pair can also be replaced with a dash, right? Now we have a dash between our two hydrogen atoms. And this is called Cooper notation. So if they ask you to draw a molecule in Cooper notation, you write it with just a dash between your two molecules, or your two atoms, I mean, right? Okay, but this dash, what does this dash represent? The bonding pair. So 1 dash, 2 electrons. Okay? 1 dash, 2 electrons. Okay, because for a covalent bond to form, 2 electrons must be shared between 2 or more atoms, right? Okay, you understand that? Okay, let's do another example.
It can be more than one dash.
Hmm?
It can be more than one dash between the atoms.
Yes, there comes double and triple bonds, but I don't think you learn about it this year, only next year. Okay, so let's do hydrogen plus, okay, chloride. So hydrogen has how many valence electrons? 1. Okay, how many does chloride have? Ooh, 7. Okay, we'll see now why it's 7. Okay, so remember, if you must, the first step here is determine the number of valence electrons. Now this is something I've shown you, I'm showing you again so you can remember it. If we want to determine the amount of valence electrons for any atom of any element, right? If we look at magnesium, for example, we go back in the periodic table. So we go from magnesium, sodium, and then we get to neon. Neon is our noble gas. They are perfect, right? So if we want to determine the amount of valence electrons magnesium have, we take magnesium's atomic number 12 minus neon's atomic number 10. So magnesium has 2 valence electrons. Okay, let's look at chlorine now. Okay, chlorine has 17 atomic number. So we have 17 minus 10, right, to give us 7 valence electrons. Okay, so if we do bromine, for example, it would be 35 minus 18. Okay, which would give us 17. Okay, we can do this with anything here. Let's do lithium. Lithium's 3 minus helium's 2 is 1. Lithium has 1 valence electron. Okay. So those are our valence electrons, right? They are the amount of electrons in our highest energy level.
Then what are those orange numbers?
Okay, so they are also charges. They are exceptions in our transition metals. Okay, so they are exceptions. Otherwise, all of the transition metals will be positive 2. Sorry, just let me take a sip of water here. Okay, so we're going to finish this one, and then tomorrow I want you guys to bring the previous chapter with you if you don't have it with you, right? The one where we drew the AFBO diagrams for all of our molecules, of all of first 20 elements. Okay, so we just said, I'm just going to change this up, make H and X. We said chlorine has 7. Okay, so if we draw chlorines, we start with 1 on each side. So we go 1, 2, 3, 4, 5, 6, 7. Right. Okay. So now this electron over here is going to fill up this spot. Because this spot only has 1 electron, while all the others have 2. So that means, then we draw our arrow. Then we draw the molecule together. So we have H and X. And then our dot for the Cl. Like this. Okay, so we are going to do some examples of this in the following 2 pages. Okay, but let's just quickly, let me show you something. Yes.
Ma'am, you want to count the dots?
Yes.
Make sure it's right.
Yes. Okay, so how does chlorine's AFPO diagram looks like? Okay, so chlorine, first of all, element number 17, it is in the P block, and it is in our 3rd period. Okay, so we know we have to draw up until 3P. Okay, so we start at the top with 3P, then 3S, then 2P, 2S, and 1S. Okay, so 1S, 2S, 2P, 3S, 3P. Okay, we have an atomic number of 17, that means 17 protons. Okay, if it's a neutral atom, that means 17 electrons. So now we can fill in our electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Okay, that's our AFPO diagram for chlorine. Okay, now we can see, right, it is 1 electron away from being happy, from being perfect. Okay, so that's why it bonds so nicely with hydrogen, because hydrogen has that 1 electron it wants to put in here. Okay, you understand? Right? So it's 1 electron away. So even though there are 7 electrons in our 3rd energy level, okay, it's 1 electron away. It wants to gain 1 electron, and that's why its charge is -1. Okay, that's how we got the numbers at the top of our periodic table. We see chlorine is 1 electron away from being perfectly happy like it wants to be, right? So that's where we get -1. So even though it has 7 valence electrons, the charge would be -1 because it's going to gain 1 electron. Okay, so that's where we're going to stop for today. Okay, and then tomorrow we will do the examples. Okay. Yes.